We've taken the hardest system we could imagine, which is to understand multiphase flow. We know that the behaviors we get are different whether we're dealing with a fluid that's lighter than water or denser than water as to what it looks like. This one that we've used here has always been a DNAPL, one that sinks through water to reach some kind of equilibrium. And so far we've talked about two important features. One is the capillary pressure saturation behavior, which describes or defines the architecture which we would see it here. There's enough information in the capillary pressure saturation curves to define exactly what the distribution should look like. And most recently, maybe in the last couple of times we've met, we've talked about the rates at which we can remove it from the subsurface. And so we'll probably finish up largely our discussion on multiphase flow today. And then we can start talking about the other part of this figure here, which is on the left-hand side of the plume where the groundwater is coming in, it's pristine, and on the downstream side, it's not. And so we'll talk about the transport of the dissolved components is our next transport mechanism to talk about. So that's kind of where we're going with this. If we go back to here, okay, so these are what we might talk about today. I thought I'd spend some time talking about actually go through basically the components of assignment 4, just so we know, because it encapsulates most of the points that we've made so far. And then we'll make some kind of broad discussion and broad description of how non-aqueous phase liquids may move in the subsurface, whether they're lighter than water or dense or heavier than water, and what the ramifications are from the geometries of the chimneys that result, and the saturation profiles and the locations of the puddles, etc., and how we might measure those in situ. But first, it might be good just to cap everything off by rolling things into a single package related to relative permeabilities, which is what we've been talking about most recently. So the recap, I guess, will be that. So this is basically, well, it's not basically, it is assignment 4. And so what we might do is just go through so that you have in your own minds exactly what you might do for this. And so it's all related to our ideas of relative permeabilities. And so the crux of this question, you don't have to read it, you can read it if you wish. The crux of this question is to figure out exactly what the rates are that water will flow through this sample if you set it up as basically a flow test. So you have a sample that is constricted on 4 sides so that the flow will occur through it. The flow is driven by this supernatant fluid on top of it, which saturates the whole sample. And you can imagine that if you put something in a bucket that has a hole in it, it will drain out of the bottom. And so this is no different. So this is looking where the flow will occur through this sample. And the sample happens to have 2 features. It actually has features that look a bit like this, right? You can imagine it looking like this. So if this is the chimney on one side, which is saturated with an apple in here, and outside here. It just happens that in this case the flow is from left to right, and we're going to look at flow that occurs downwards through a system. So that's the only difference. But this stripe that goes down through the center of our sample is really reminiscent of this chimney that we have within the system. So this is this. So this is the stripe that goes down the center. So we want to, the question basically is to say, how long will it take for us to dissolve this thing out and carry it out through the bottom of the sample and thereby clean the sample by dissolution? And so the first piece of information you need to be able to do that is to realize that, we've said this once before, is that if you're looking at mass flow rates, then you can get the mass flow rate from the volumetric flow rate multiplied by the solubility. So this is in volume per unit time. This is in mass per unit volume. And so the product of these clearly is a mass flow rate, which a mass of TCE or a mass of any kind of compound we have. So to do this, we need to know exactly what Q is, bottom line. So what do we know about Q? We know that Darcy's law for any system can be written as a cross-sectional area of flow, bless you, a relative permeability, a viscosity of the fluid, and a pressure drop. In this case, in the z direction. It's not and so we have to remember the fact that when we're dealing with this, we had this long discussion about whether we would use pressure gradients or head gradients. We know that this isn't completely right, because in the vertical orientation, if we have a pressure gradient which is finite, it would suggest that we have flow. But if it's just a hydrostatic gradient, there will be no flow. And so what we need to do is replace this in the easiest possible way. We know that pressure is equal to head multiplied by unit weight, rho g. And so we could replace, bless you, we could replace this term by dp dz, could just be the change in head times rho g. So all we're going to do is going to replace this term here with this. And so if I write that out in longhand, so that all components are here, and then we'll talk about what each of these individual terms are. So that's the basic expression we need. And so we just need to figure out exactly what the individual terms are. And so if I go back to here, and I won't bore you with exactly what you're given. You're given a permeability of the sand, so you know the permeability. You're probably given a viscosity of water, which is this. You know the density of water. No, you're not given, but you know that density of water is what? I'm trying to think what else is in this expression. You know, yeah, I think you know everything else in the system. Don't know why I didn't write this in. So if we were interested to know exactly what comes out of this, then what do we need to know? You can imagine that there's a portion that's coming out of the, so there's a stripe of this material here, and the other thing that you probably, we know is an initial saturation, which I'm looking for, but I don't see it. I guess I see it here. So this stripe has an initial saturation of 10%. So it means it's 90% water and 10% NAPL. The NAPL is TCE. And so if we wanted to calculate the flow rate out of here of water, let's do the easy one first. So let's do the part which is the water coming out of here and out of here together. So what would be the components of this expression for this? So the part that's 100% water saturated. And it's all very straightforward. There's only a couple of tricky parts. And that would be volumetric flow is going to be an area, a relative permeability, a viscosity, oops, a head gradient, and rho g. It's for water, so you could imagine what the components would be. So what is going to be the area? The area is 5 centimeters by 20 centimeters twice. So it would be 0.05 times 0.2 times 2. I guess that would be meters squared, right? This is meters, and this is just two segments that have it. Just adding those two together. What's the relative permeability when it's 100% water saturated? Probably don't have to think too much about that, right? Well, let's do it anyway. So if it's 100% water saturated, then this is the relative permeability of the wetting fluid. This is the relative permeability of the non-wetting fluid. So 100% saturated, you'd expect it to be 1. We have permeabilities of the material, which is a single value, and we have viscosity of water. And so if we have each of those, the permeability was 10 to the minus 6, was it? The viscosity was, I think, 10 to the minus 3 Pascal seconds. This is meters squared. I'll zoom up to make sure that those are the right numbers. Yeah. Oh, 10, oh, that's not right. So what's 10 to the minus 6? So I guess we would have to multiply that by 1 meter squared is equal to, so 1 meter squared is equal to 10 to the 4 centimeters squared, right? 10 to the 2 times 10 to the 2. And so I suppose we'd have to divide that by 1 meter squared over 10 to the 4 centimeters squared, which would be 10 to the minus 10. So so far we have this, which is here. We have this, which is here. We have the ratio of these two. I think that's right. And so there's the tricky part, which is dH/dz. And we have rho, which is 1,000 kilograms per meter cubed, and 9.81 meters per second squared. So we have everything we need to be able to calculate the volumetric flow rate. You can check the units, except for this one term for the head gradient, which we've cast. And so what is the head gradient that we need in here? It's the change in head that occurs over a length. And if we were to look at exactly what that would be, then what would that magnitude be here? So the flow is occurring between this point here and this point here. And so if I draw it off to the right-hand side, it's a bit easier. This is the length of flow. So this is dz, if you like, which is conveniently 0.5 meters. But what's the magnitude between the heads at the bottom and the top? So if you look at this point here, and if we choose z equals 0 at this particular point here, then the head is equal to the pressure head plus the elevation. The elevation by definition is 0. What's the pressure when it comes out here and drips out? It feels atmospheric, right? All of a sudden it drips out. So this pressure here would also be 0. So by definition, on the bottom, the head is equal to 0. If we look at the top and look at the same relationship, the head at the top is equal to the pressure divided by the unit weight plus the elevation. And so we know that if this is our datum, this point here, then going up 0.5 meters, this is the physical location of this. Actually, why don't I just draw that in? This length here is 0.5 as it was on the other side. But the flow is occurring from this point, and clearly the pressure isn't equal to 0. It's equal to some amount due to the fluid on top of us. And the fluid on top of us is 0.1 of a meter, so this complete term here would be 0.1. And so if we want to be able to get the change in head, dH, goes from 0.6 to 0, so it changes by 0.6, but it does it over a length of 0.5. And so all we need to do is to make sure that in this particular case, dH dz is equal to 0.6 over 0.5, which is 1.2, right? Hydraulic gradient of 1.2. And so that's what's driving flow in this particular case. And so this would be the amount that would go into here. And so that, for our purposes anyway, allows us to calculate exactly what the flow rate would be through the non-striped part of this system. It's water-filled. We're looking at the flow of water through this and the volumetric flow rate. And if you do the units balance, you should find out that Q would be in meters cubed per second. Hopefully it should work out that way. If we want to do it now through the stripe, then we have exactly the same approach, right? So we can use the same approach. Let me just write out the same expression. So the part that is 90% water and 10% non-aqueous phase liquid, it's going to be exactly the same. Volumetric flow rate, area, relative perm, permeability divided by viscosity, head gradient, and rho g. We're interested in Q water. I guess we could say what Q NAPL would be as well, but this is water we're specifically interested in. What would we expect the flow rate of the NAPL to be through this? We know that we're at a saturation of 90% water and 10% NAPL. We know the relative permeability of this NAPL is 0. It means it's disconnected. It means that no matter how much we huff and puff along here, it's physically not going to flow, period. And so this is definitely going to be 0, just by rationalizing that. But what we'd like to know is the rate at which we can get this water flowing through this central stripe. And so if we want to know that, then we need to know what the relative permeability of the system is to water. And so the relative permeability will be something like this. And this is at 90% water saturation. And it is, well, it's almost a linear line, so it's roughly 90%. it's not quite. Is it going to be less than or more than? I suppose it's steeper, so it would be less than. So I don't know what this is. So in terms of this expression here, this relative permeability would be 89%, say, from the rationale. I think that's right, isn't it? If this line were really steep, coming down here, then the relative permeability would be less than 90%. If it's exactly 1-to-1, it would be 90% here. And so if it's just slightly steeper, you can do it by similar triangles, of course, but we don't need to worry about that here. So we know the relative permeability. What's the permeability of the porous medium? The porous medium has always got the same permeability. And so this is always going to be just the permeability of sand, which I think was 10 to the minus 10 meters squared. This is the viscosity of water, which we know is 10 to the minus 3 Pascal seconds, roughly. The gradient is exactly the same as it was before, which is 1.2. And this is the fluid that's flowing is the density of water, which is 1,000 kilograms per meter cubed. So that's it. And I guess the only thing we haven't said is what the cross-sectional area of the stripe is. And the cross-sectional area of the stripe is just going to be, if you can read it now, this is 10 centimeters across, 20 centimeters into the page. So this area here is equal to 0.1 times 0.2 meters squared. And that's everything you need to be able to calculate that. So that's all we talked about the last time. We talked about how we'd rationalize calculating flow rates of different fluids in the subsurface. In this, we're interested to be able to figure out exactly what this mass rate of removal of one compound is. We can do that if we assume that once it goes through this stripe, it dissolves at a maximum solubility. That's the maximum it can take out, so it would be the fastest rate that it would take stuff out. And the volumetric flow rate we can calculate if we know what the relative permeability is on this curve. Of course, as you start to remove this material, which is kind of the crux of this question, what's going to happen? You're going to dissolve the NAPL. It's held in by interfacial tensions on the grains, but as you dissolve it and carry it out, it's going to shrink. And as you shrink, you can imagine that the relative permeability that you start off with is actually going to migrate up until once it's all dissolved, you'll be at 100%. 100% water saturation because everything's dissolved out, and 100% water saturation, you're also at 100% relative permeability. And so you need to figure out a rational way to be able to do that for this assignment. We won't do it here, but that's the mechanism by which to do it. So we spent a lot of time talking about swimming pools, why there was this extra term in addition to pressure, which is the static head sitting on its own. And we also talked about the way to get around that is basically to make this substitution that we made here. And that is that don't deal with behavior in terms of pressures, but deal with behavior in terms of heads. If you deal with it in terms of heads, you'll always be right, I guess, is a short way of saying it. And because this expression isn't quite right just with this one term. It needs an extra term because we know that when we sit in a swimming pool, there's a pressure gradient with depth, but that's not moving anywhere. It's just a static pressure gradient. And so we need to be able to incorporate that other term. All right? Taking pictures of the screen. That's all right. That's okay. But you have to go back and look at them sometime. You realize that, right? Okay. Anything else? I always remember a colleague of mine saying that when you take movies as your kids, by definition, if you film more than 50% of your life, you never have any time to look at it. So, don't think that's a truism. So, anyway, all right. Moving on. Okay. So, that allows us to say something about rates at which we can move fluids in the subsurface. Want to get a picture of what? This one? Have you got it? Does it need to be really, really big? Or really, really small? I'm just messing with you. All right. Got it?
Yep.
All right. We're in business. All right. So let's talk in broad terms about maybe some slightly more, certainly all the things we talk about are practical in this class, but maybe some practical things. There's some things we don't need to worry about. I'm going to zip through these. But I guess what I would like to do is talk in and make differential comments between behaviors for fluids that are lighter than water and those that are denser than water, because they behave, as we can imagine, differently in the subsurface. We know that those that are lighter than water, if we look at the geometry in the subsurface sitting on a water table, then we get this chimney, a lens that sits on top of the water. This is the ground surface. This is the water table. And we know what all these components are, right? This is a chimney that has a saturation of the NAPL, I don't know, maybe 30%, maybe less than that. It gets less at the top, and it gets more saturated as we get down. This saturation here would be at the saturation of the NAPL would be at about 1 minus the irreducible saturation of water. In other words, it's pushed all the water out, it's filled up all the pore space except for the irreducible saturation of water, and so it's probably at 80% or 85% NAPL in this puddle that sits here. It's buoyed up by the fact that it has water underneath it. It's less dense than water, and so it is being buoyed up by the water and physically sits on top of it, in the same as a monomolecular sheen would sit on the top of a swimming pool if you put gasoline, if you're silly enough to put gasoline in the swimming pool. And that's the behavior we'd expect to see here. And contrary to that, if we had a very similar geometry for a denser than water fluid with an underlying capillary barrier, then what we'd expect to see would be this, with exactly the same characteristics, if you like. So this again would be this partially saturated chimney that's smeared, maybe at 30% or so. It doesn't matter whether it's above the water table, which is this part here in the vadose zone, or below the water table. It would still have this NAPL as a chimney. If it's below the water table, we know that in this case, because the groundwater table is sloping towards the right, that we would get flow in this direction, and this would be carried downstream as a plume, just as we talked before. And we know that the mechanism by which this high NAPL saturation component has been arrested hasn't been by the water table, which is slipped right the way through, but it's being arrested by this capillary barrier. And so this is the reason that it stops at this particular location and would rest in place. So let's talk about exactly what, from our understanding of these two very important component behaviors, most important of which I guess is the capillary pressure versus saturation curves, exactly what we think the saturation distributions might be in each of these cases. So that's what we'd like to look at, what those would look like on graphs per se. And so this is the key view, I think, of that. We know that, and this is out of Fetter, so you've seen this elsewhere. If we look at what the pressure with depth distribution looks like, it would look like this. So this is the water table here. This could be the ground surface, I suppose, here. And this is our saturation of water that we've talked about many times, between 0 and 100%. The physical meaning of this, what we've referred to before as, we've often called this a bubbling pressure, PC0. If we divided that by the unit weight of water, then this would be a height. And this physically would be the height at which you can hold the water up. It's in tension. By definition, at the water table, the pressure here has to be atmospheric. If we're going upwards in height, and we've drawn this a number of times before, this is Z, this is P. If we're going upwards, then we'd know that below the water table it's like this, above the water table it's like this, and I guess we know dz dp. We know that the change in pressure with elevation is equal to the unit weight. Always true, irrespective of whether it's a liquid or a gas, as you know. This happens to be a liquid, so this would be the unit weight of water. And so this would be in tension at this. So that's why it's called, the capillary fringe is sometimes referred to as the tension saturated zone, because the water above the water table is actually in tension. If we look at these behaviors, we can define the behaviors in terms of things that we've referred to them before as. So this is always going to be this is the saturation of the non-wetting fluid, which in this particular case is air. And this is going to be the saturation of the wetting fluid, which in this particular case is water. And so that's physically what this diagram means. So it's essentially 100% saturated except for maybe some residual air which is in the system. At this would be the irreducible saturation of the non-wetting fluid, which is air. And physically, as we go higher up, we get less and less water and more and more. Our benchmark in terms of what we'd expect. So if now we could calculate this height rise if we knew the entry pressures. So if you wanted to, what do we know? We know that at this point here, we know that this capillary pressure curve is equal to what? No number? Talked a little bit about last time. And so what this means is that if we know the permeability of the medium, which we often know, we just did in the last example we did, if we know the porosity, if we know the interfacial tension, then the only thing that we don't know is pressure. And so we could calculate that. And if we now know pressure, we would be able to calculate, for instance, this height rise that occurs here. So in other words, we could, if we knew some material properties of our medium, we could calculate the height of this capillary fringe, should we wish to do that, just from what we know so far. So what we're interested in doing now is what happens if we spill something into the top of here. What will physically happen? And how does that relate to what we know about saturations? And so this is just an example of exactly that. So these four little cameos are exactly this picture here. And it means that we're pouring material in through the top. It starts originally with this profile, and this is the capillary pressure versus saturation curve. You'll notice this is out of Fetter, if you have Fetter's book. You'll remember that before we defined water content, which is equal to volume of water over the total volume. as opposed to saturation, which is the volume of water over the volume of the pore space. So in other words, the water content is the total volume of the soil, including the grains, whereas the saturation refers to only the pore space. And so if you look at this axis here, this would be a saturation of 100%. And this would be a saturation of 0%. Same figures, they just repeat themselves. I can't do here. And so this saturation here, if it's the volume, if all the water is filling the void space, then this magnitude here would also be the same as the porosity. So in other words, the porosity of this particular system is going to be this is 0.3. So all by way of saying that this is just a different horizontal axis, but it's exactly equivalent to saturation, just a different terminology that's used. And so these three conditions are for, this is the first one, pristine. This is when you start putting gasoline into here, spilled from the surface rather than from an underground storage tank. And in the same way that we talked about what these individual components represent, and I suppose we can also note that the saturation of water plus the saturation of NAPL plus the saturation of air have to equal 1, even though this isn't quite saturation on the base, but that makes sense, right? We have only so much space to fill. We can fill it with water, we can fill it with air, and fill it with NAPL. If we have less NAPL, then we probably have more air. And so that's physically what this represents. And so if you look at what this would happen, you'd imagine this tongue with time after 2 hours, after 8 hours, looks like this. So this now is this tongue that is partly saturated. So this, what is, in terms of this is probably 20% saturated, right? And this is probably 70. And this is probably 10. So you have this coming down here. You allow it to play around for a little more, and it ends up reaching some equilibrium condition, which is this. And so if you think about what this equilibrium condition is, then it's really these geometries that we've been drawing all the time. So we've drawn this geometry of, if I draw it to scale, if I can draw it to scale. So this is the ground surface. This is this chimney that goes down here. This is the water table. This is this lens that sits on top of it. And this is this smeared zone that goes down through here. This is saturation of the NAPL is maybe 20% or 30%. We can have a look in a second. This is maybe 80%. And if we draw, I guess, a section across here at some particular height, like this, then you see exactly those components. So this first part is water. This second part is NAPL. And so together, this is what physically this would look like on a capillary pressure versus saturation curve, kind of. And physically, what it would look like in situ would be this lens that sits here, which is this big portion here, which is just buoyed up on water. And once you get above this, you have this chimney, which is at relatively low saturations, which is just this smeared zone that's left some residual stuff as it's come down through here. It's left its mark as it's then accumulated in this bucket on the bottom, where it can't go, bless you, where it can't go any further. And so that's really how you translate our physical description of these capillary pressure versus saturation curves into physically what's going on in the subsurface. That's all. I guess the couple of other ancillary things that are maybe worth noting is that initially the water, the top of this saturation curve exists here, and this is the water table at this height. What's happened is that instead of the water table still being at this height, which is about 30 centimeters, it ends up being slightly lower at about 20 centimeters. And so that's exactly what you see here. The original water table was something that maybe went through, but because you have this height of this other fluid sitting on top of it when there wasn't any fluid before, what it's done is it's depressed this water table slightly. And that's why we have this kind of lens-like base to this thing, is because it's physically pushed the water table down from looking like this, still looking like this, but then flattening it out as soon as this stuff landed on top of it. And so we shouldn't. So all I'm trying to do is make the connection between these pictures that we've drawn many, many times and physically what the saturation profile might look like in here, because this gives us a way to quantify exactly what's going on here. And we can quantify this also in terms of the capillary pressure versus saturation curves. It makes absolutely complete sense that the saturation profile should look like in here based on what we understand about capillary pressure versus saturation curves. Okay? All right. So I think there's some description here, but it's basically saying exactly what I've just said. I suppose another exposition of this would be looking at the same, it's a different experiment, but it's doing the same thing. And that is, if you put water, so instead of measuring saturations, let's assume that in a column you could measure pressures. If you could measure the pressure through this pressure gauge at about 1 meter down, so this is 110 centimeters, so this is about a meter depth, this is about half a meter depth, this is about 20 centimeters down. If you could measure the pressures at each of these locations, then would you be able to interpret physically what's going on here? We have these pressures measured, we could draw a straight line through them. We know that by definition, the definition of the water table is where the pressure is atmospheric. So this is, atmospheric is gauge pressure of 0 centimeters of water, right? You remember that gauge pressure is equal to H W by definition. Just our definition of pressure head, right? So in other words, a gauge pressure in centimeters of water would just be this expression here. So this is not mercury, but just gauge pressure. And so by definition, if the definition of the water table is where the pressure is equal to 0, this is where the pressure is equal to 0. So by definition, this has to be the water table. Above this, we have this tension saturated zone. And so let me just zoom up here. Right? Well, I guess we did it on this. This tension saturated zone is where there's enough tension in the water to keep it fully saturating the porous medium. And so if we were to draw this capillary pressure curve versus saturation here, then this is what it would look like. It would look like this. It would be %, saturated, 0% saturated, and this would be P C0, this term here. So this is physically what it would look like in terms of pressure space. Actually, we've drawn this diagram before. But now what we're going to do is we're going to dump some gasoline into it. And I guess the order of doing this would be, this is the first case. You push stuff in through the top, which is here, and it changes the pressures. So these pressures here of a liquid, so you're measuring pressure of a liquid. It doesn't care what the liquid is, and you don't know what the liquid is if you're just measuring pressures, and so the pressures change to this amount here. You keep on putting some more in, and the pressures change to being like this. And finally, like this. And so how do you interpret this? Well, by definition, this is this capillary fringe, which is now being compressed by this other fluid that's moving down here. Now you have two places where potentially the water pressure goes to 0. One is here, and one is here. And so since by definition the water table is where the pressure is 0, there are two tables, water tables. You can decide whether they're water or not. But this one here is definitely water. But what it's doing is that the oil that's coming down on here, gasoline above here, and water below, is it's compressing this capillary fringe and giving you an oil table and a water table. So this is the interface between a partially saturated zone and oil, and then a tension saturated zone of oil above it. And here this is the capillary fringe which is being compressed. As you keep on adding some more fluid to it, then you get these two distinct behaviors. One is that you have a portion which is saturated with oil. So again, this by definition is a water table. By definition, atmospheric pressure. And this is what we might refer to as an oil table. And in between here, we have a portion where it's saturated with oil. So we could look. So this is the material here that we'd like to be able to remove at some saturation. So this is gasoline, if you like, or what we've called an LNAPL. And so the reason for spending time on this is because what we'd like to do is be able to calculate exactly what this height is between these two water tables, the oil table and the water table. And if we know what that height is, we know what the porosity is, and we know what the saturation is, we have some information about exactly what the mass of material is. And so what we could do is then go through a thought exercise as to what this physical system would look like if we just draw a cartoon to represent it. And this cartoon is this. So we have this lens that's sitting on top of the water table. This lens is almost 100% saturated with the lighter product, minus the irreducible saturation of whatever else is in there. But we know that if we drill a hole through this, the hole will just fill up with the stuff that comes into the hole from outside, and we want to be able to make sure that the depth of this that we measure in the hole is really the depth of this thickness of the product which is in the aquifer in reality. So I guess that's the issue that we have to deal with. Because we know that we have this thing with an oil table and a water table, we'd like to know that if we measure something in a borehole, which is this particular depth here, we'd like to know whether this is the amount that we measure in the borehole or not. And so we have to ask ourselves that question. So this is the geometry that we would think about. A lens that sits here, a drill hole that goes through it. This green stuff will leak into the hole, and we'll end up with the height of the free product sitting on top of water in the well. If we put down a depth sensor that measures the electrical resistivity difference between these, we can pick up this interface, so we can measure this thickness T relatively straightforwardly. We know that at the interface between the column in the borehole and the fluid below it, the pressures have to be equal, and so the pressure on the oil pushing downwards and the pressure on the water pushing upwards have to be the same. We can calculate exactly what those are if we look at the geometry of this. So the pressure of the oil is just going to be the height of the fluid here multiplied by its unit weight, which is this. Density, gravity, so this is these two together are the unit weight of the oil, and the thickness. But we know that the pressure acting upwards here is in communication with the reservoir, and we know that there's an oil table that sits up here, and we know that there's a water table that sits down here. We know that by definition the water table is somewhere where the pressure is atmospheric. And so if we go down from this to the bottom of this hole, the pressure acting at W is just going to be this. It's going to be equal to the unit weight of the fluid multiplied by W. W is this difference. This is the water table. This is the depth below the water table. So this magnitude here is this false depth. And so if we equate these to each other, because they have to be the same across this interface, we end up being able to calculate exactly what W is. And so what's important, I guess, to know is that if you measure the thickness of this thing in a borehole, it actually isn't the true thickness. The true thickness of the stuff that's sitting in the aquifer is something that's less than that. And so the true thickness is the measured thickness multiplied by this ratio. And this ratio is going to be something like a thickness. The density of oil might be 800 over 1,000, say. So it's 80% of this magnitude, not 100%. And so that's important if we want to be able to figure out exactly how much material there is that we're going to use. And so it's a very simple calculation to make. It only depends on the relative densities of the two fluids that are sitting there. And it is a direct consequence of the fact that we end up with a water table and an oil table. And by definition, since the definition of a water table is where the pressure is zero, we can calculate the pressure of this interface being equal to just the height of this water column. Okay? And so, if we wanted to calculate the total amount of fluid that was recoverable, then one way to look at it would be to do two things. We know that the thickness, the true thickness of this is just the thickness minus the height. So in other words, this green thickness here is just T minus W by definition. If it's over an area in plan view that is A, then this is the total volume that is included. This is, if you like, uppercase V. The volume of the pore space we get by multiplying by the porosity. And so the total volume of the pore space is this. And so if we want to know how much fluid is in here, then it's going to be the total volume of the pore space, which is this. V pores, multiplied by the saturation of the NAPL. And the saturation of the NAPL is just going to be 100% of the pore space minus the amount of water that has to be left in there because you can't get it out, which is the irreducible saturation of water. So this is probably 10%. This is 90%. This is probably 30% as a ballpark number, and then this is just a multiplier on the rest of the volume of the green volume that would be here. Okay? And so if you want to see that in a geometry that kind of hopefully makes sense to us, then that geometry would be this geometry underneath here. And so what we've just done is this calculation here is just the volume of the aquifer, the pore space in the aquifer. And this term here, if we looked at the distribution of these fluids in the same way that we looked at this, if you just go back here. So remember that we divided this up into water, NAPL, and air as we go down through this column. So we could do exactly the same things in this figure here. Going too far. Here it is. This is what it would look like. So as you go down, this is the irreducible. So this is height, similar to capillary pressure. You could think of this as a pressure, if you wanted to, equivalent to elevation. They scale with each other through the unit weights of the fluids. And if we went up through here, then this is the oil table. The green stuff that is present is going to be, this is the saturation of the NAPL. This is the saturation of the water, irreducible. And so this is 1, 100% saturated. So 1 minus the irreducible saturation of water is this here. So this is just this. And so in its simplest form, we can multiply the volume of the aquifer, which we now know that this height is going to be equal to T minus W, not T, but T minus W. And if we multiply that by the porosity, then we get the volume that's there. And so this is slightly idealized because we know that as we go up to the ground surface, then the proportions of these different components, the saturating oil and the air and the water, will be present in these percentages as we go up, just as they were when we looked at these figures here. So there was a portion which was water, a portion which was air, and a portion which was the NAPL. And so we have all three of these components present as we go up through the system. And that's exactly what we have in this particular case. So what we could do is we could ignore this part that's here. And the reason we can ignore that is because there's going to be a part which is down at this portion here, which basically corresponds to this. So x1 and x2 are roughly the same as each other in terms of these two areas. And this is because there's a portion of water trapped in the capillary fringe here. Not important for us to really know that, I guess. But so if we want to use this simplified way of calculating the volume that's present, which is what this is, then this green volume here is just the outline volume in this whole thing here. It's nothing more than that. It's the height multiplied by the porosity, which is the void space, multiplied by its areal extent. So that's the total volume of the pore space in the aquifer, and the saturation of the NAPL that's present within it, just a proportion. We ignore the fact that this is here because there's a portion above it which looks just the same as it. And so x1 and x2 compensate for each other, and so this actually isn't a bad estimation of that magnitude. So in other words, we were able to calculate the volume. If we wanted to know how much of this we could recover, what proportion of this would be recoverable? Is the answer on that phone? Not looking straight over you. No? Well, all right. So if you want to know how much you recover, so this amount here would be irrecoverable, right? So the recoverable amount, well, you're still dealing with the same volume of the aquifer and its porosity, so still this. But what's the amount that can be removed? You know that the amount that's in place is 1 minus the irreducible saturation of water, which is this amount here. But this amount here is going to be left in place because this is the smear that you can't get rid of. So minus this. So this is the total amount that's in place. This is the total amount that will be recoverable because you'd leave this portion in here even after you'd sucked everything out of the system. So I guess it shouldn't go above the water table. It should just be this height here. It should just be this height, T minus W. So we can calculate how much we could remove as well. All right. In Fetter, there's a very, the reason for kind of showing it in this way is that the curves on these are really capillary pressure versus saturation curves, right? And so if we know how to represent these capillary pressure versus saturation curves, then we should be able to figure out exactly what these volumes are underneath it. And so there's a very involved derivation in Fetter's book that does that. And maybe it gives us reason for using, if you remember what we talked about in terms of Brooks-Corey relationships. And that was that we could take these individual curves that we had for capillary pressure versus saturation. And we could use those, we could translate them into something that looked like this. And it was exactly the same as this figure here. Capillary pressure and with log saturation. And so in other words, you might remember that we could convert these capillary pressure curves into something that represented just the equation of a straight line in log space. And so if this equation of the capillary pressure curve represented in this particular way does represent this behavior, and if this behavior is what it looks like in the subsurface, then maybe we could use this particular curve here to say something about this distribution. And so the derivation in Fetter's book basically does that, to be able to calculate exactly what that is. So it uses this idea of having a thickness of oil. The thickness that you measure in situ is, in the borehole, is much deeper than it is within the porous medium because of the reasons that we've talked about of having a water table with an oil table on top of it. The distribution of the different components as you go down in depth is given as this. If we can represent this distribution by Brooks-Corey, then we can come up with some equations that represent the amount of fluid in place. And it turns out that they come out to be very close. But the two expressions that we have today use many times, I think. Okay. All right. So we know that in situ, the depth of material that we have in place is going to be different in a borehole than it is in the aquifer. If we're talking about other mechanisms by which this stuff can be spread, then we know that since this stuff sits on the water table as a lens, if we drew the saturation versus depth distributions for these, we'd get something like this. In the residual zone, we have a little bit of NAPL. We have a little bit of oil. We have a lot of air, and we have a little bit of water trapped in here as well. As we go deeper, we end up being in a place where all of a sudden the oil is at its highest saturation, which is here, this little lens, which represents this stuff here. And below that, we have water. So this is everything below this red curve, I guess, is water. Air is in here, and NAPL, which we've done as green before, is the stuff in here, which is at relatively high saturations at this point here. If the water table for some reason goes down, what it would do is it would drag this stuff down with it, with that lateral extent. It may spread a little bit as it goes down, but what it would do is that now this chimney that was here is now extended by the fact that this physically goes down through the system. The new distribution would be oil everywhere underneath this green line, saturated at a relatively high lens here, water everywhere below the red line as it migrates down. And if seasonally the water table is buoyed up again and it comes up again, then all of a sudden this would be the distribution. So now this is water, and we're left the boundary here. So what we have now is a lens which is at relatively high saturation, which is sitting here and goes down to some depth, I suppose. But here we have this smeared zone. And this smeared zone is really just the same as the zone that's above it. And so what we have now is a much larger volume of here, which is at relatively low saturation. Maybe the saturation of the NAPL is, well, you can see from here, it's 20%. And now, when water gets carried through here by the action of groundwater, due to the head gradient, then what it will do is it will dissolve this stuff and travel it downstream. And so actually, coming back to where we started off today, it's really not very different from this physical system that instead of things moving vertically, this is just switched on its side. It's traveling horizontally. We have a flow that's going along here. It's going to dissolve material out from here, and it's going to transport it downstream, and it's going to take it to some compliance point, which is down there. And so having this rise and fall of the water table is actually unfortunately, quite an efficient way of distributing this stuff below the water table, where it couldn't actually get below before because of buoyancy. And it's just driven by the fact that between summer and winter you might have different elevations of the water table system. Okay. We don't have, when does this, oh, we don't have any time left, actually. Let's just finish off on this one figure here. 2 seconds. So if you imagine the behavior that we've talked about for denser than water fluids, in the same way that we talked before, if it's able to get through the groundwater table, you can imagine that this capillary pressure versus saturation curve, so this capillary pressure versus saturation curve is now inverted from how we had it before. If you think about this, 0 to a large number, and if you imagine this as being flipped, this is exactly the same curve but upside down. So this is a large pressure, this is a large pressure, and if you think this is just a mirror image of each other, so they're flipped, then the behavior you have for a DNAPL is exactly the same. If you look at the capillary pressure versus saturation curve, 0 capillary pressure, large capillary pressure, saturation of water from 0 to 100% here. Then if you look at the distribution along this curve here, this would be the saturation of water, and this magnitude here would be the saturation of the NAPL. In this case, DNAPL. And so you see exactly the same behaviors. Here would be a large saturation of NAPL, and it would be the equivalent of this puddle, if you like, sitting at the bottom of the aquifer because it's found its way down through here. It's left a smear zone as it's come through here, and this would be the small amount of water that is present within here. As you go higher up within the system, there's a large amount of water, and there's a very small amount of NAPL, which is this smear zone. And so I guess the only point I'm trying to make is that the architectures that we've talked about of these different systems is really a consequence of the physical behavior that we understand through these capillary pressure versus saturation curves. And so when we look at this behavior with a smeared chimney and a whole bunch of stuff sitting at the bottom in a puddle, then that translates exactly to this distribution of saturations as you go down through the subsurface. So just trying to rationalize that. Right. Okay,